chapter? You want this topic, no?
The system of resistors.
Okay. So initial part is not problem, is it? System of resistors. Yeah, we have one resistance. And the symbol for resistance is this one, right? Like zigzag line.
Yes, sir.
Okay. So if you have single resistance and we can measure the voltage across it. We have a single resistance. Okay. And there is a voltage source. V. The resistance value here says R. Okay. So this current, right? There will be a relation between this voltage and current. So if you increase the voltage, what will happen to the current?
The current also increases.
Yeah. So, and the increases by according to straight line. Okay. See, even if you have a curve like this, that's also increasing.
Okay.
Okay. So the simplest increase is a straight line, but fortunately it's a straight line for low current values. Okay. So this is V versus I for this resistance. And the slope of this thing is what? Slope equal to? Is it R?
So
What? It's
I
is y by x, no? Or delta y by delta x. So it's
okay, sir.
1 by R.
1 by R.
Okay. Slope is V by I. Okay. If I plot on the V vertical axis, then it is slope is 1 by R. That depends on what they have in the book or whatever.
Okay.
In the exam, if they give it ulta means you have to do 1 by R. Okay. See here, I versus V. Okay. So take the slope, it will be 1 by R. Okay.
Okay, sir.
But depends on what they have. Usually, the reason I told you, right, for plotting I on the y-axis, why is it plotted on the y-axis instead of axis? I can also plot it. This x-axis is basically independent variable.
Yes, sir.
X-axis is independent variable. Independent variable, right? In math.
Yes, sir.
And dependent variable. Independent variable is the
Why?
thing where you can change the values freely. Okay. Dependence depending on this one and the resistance value. Okay. Here in the voltage source, whose value can be depending on the well, I mean, there are variable voltage sources. So I can raise the current. Like input. Where I can adjust. This is the response, it's output. Proper way of drawing is I in the y-axis and in the x-axis. If it is ulta means then resistance
the Y will be changed.
yeah, resistance will be R then. Here for this plot, resistance is 1 by R. Sorry, slope is 1.
Resistance.
Slope is 1.
Slope is 1.
Slope is 1 by R. Resistance is 1 by slope. Okay. So now instead of one resistance, I have two of them. R1, R2. Okay. And this voltage source. This voltage should be a variable voltage source. And this current will into that. Only then I'll get different points, right? If this voltage is a 10 volts, then it'll be just 1 point. I want this point also. So this should be a variable voltage source so that I can change and find the how the current is changing.
Okay.
So similarly, if you have this one, the idea is I can increase this one by a single resistance. To have the same VI. If you draw V of this one, where it's a two separate distance, will be some line like this. Okay. If you draw for this one, will be exactly the same line. For that to happen, this R should be equal to
this R1.
So this resistance is called series. Series means whatever current is flowing in the first one, the same current should flow in the second one. Because whatever current is flowing, it's not going anywhere. No, it's not getting diverted. So whatever is
Yes, sir.
flow to R2 also.
Mm.
That means the resistance are in series. So the drop from here to
Mm.
here,
Mm.
V1, and the drop from here to here, it's V2.
Mm.
So this V is the rise from here to here.
From the resistor. No.
So this
I mean,
apply
voltage.
voltage, yeah. Across the resistance, there will be
Uh,
voltage according to Ohm's law.
mm.
And from here to here, there is a voltage rise.
Um.
Correct. Because you're going from
Yes.
negative to plate.
Mm.
And here there is a drop because current is flowing in this
Mm.
direction. It have to flow from higher potential to lower potential. So this is high
Um.
lower potential, this was higher potential, lower potential. So there will be a drop along the resistance in the direction of current flow. Okay.
Mm.
So you know KVL, right? Okay.
Yes, sir.
So sum of voltage drop in this closed loop should be 0.
Mm.
So from here to here, there is a rise of V volts,
Mm.
and then there is a drop of V1 here. If I take it
Mm.
as positive and drop as negative, that should be equal
Oh,
to
if the V is positive, then if goes to V1, it will be negative.
no.
Uh,
In the resistor, in the along the direction of the current flow, there will be voltage drop.
mm.
That you can take it as a fact.
Okay, sir.
So this is the direction of the current flow
Mm.
in the resistor. So along this direction, there will be voltage drop.
Mm.
Okay, that's the property of resistor. So here also in the along the direction of the current flow, the second one, there is a voltage drop of value V2.
Mm.
Okay,
Mm.
then you're going from negative plate to the positive plate. No, so that's it.
Ah.
You're getting this rise.
Okay.
All dash, long dash. So from here to here, there is a voltage rise.
Okay, sir.
Okay, that rise value is V1, V, supply voltage. So
Mm.
this loop, from here to here, there is a rise of V, and there is a drop here. If we
Mm.
take, if we use the convention, rise is positive, then drop should be,
Mm. Negative.
uh, and the second V2 is also drop, so minus V2. So that this is the total this
Mm.
thing, that should be equal to 0.
Okay.
So from this, I get the important thing that V1 plus V2 equal to V.
Mm.
And this V1
Mm.
I can write in terms of the current, because what is same for both
Mm.
R1 is the current.
Mm.
Okay, so in terms of current, I can write as I R1 plus same I R2.
I R2
Uh,
and then I R3.
okay. So in this right circuit, if I use that same thing, I can get V equal to R into I.
Mm.
According
Mm.
to Ohm's law in this one. But I have said since it is
Mm.
equivalent, equal means V and I are same. So that means
Mm.
this V and this V are
Mm.
same, and this I and this I are same. So compare
Mm.
this, I'll get the result R equal to
Mm.
R1 plus R2.
R2. Oh.
Okay, only if this single resistance is sum of these two individual resistance, the VA characteristics of these two will be same.
Mm.
Basically, the VA behavior of this circuit and the right circuit should be same. For that to be same,
Mm.
single resistance value should be equal to the sum of the individual this thing.
Mm.
So this can be extended to more than one resistance. This is the third
Oh.
one, R1, R2,
Okay.
R3.
Mm.
Then you just have to add them up.
Okay, sir.
So R1, R2, R3,
R3.
R2, R3. If you have to replace it by a single resistance,
Mm.
R equivalent, and what the symbol is, use R equivalent to RS, whatever it is.
Ah.
That's equal to R1 plus R2 plus R3. So this
Mm.
gets into n resistors. Actually,
Um.
Rn. So you just have to add them up to Rn. The important thing is whatever current is flowing in the first one, the same current should flow in the
Mm.
second, same current.
Second.
So it
Okay.
should not be, suppose if it is like this, then it's not valid.
Mm.
Suppose I have a circuit,
Oh.
then this full combination I will take as a single resistance. Then it's possible to
Mm.
take this combination and this other things are in series.
Almost it should be in a straight line, sir.
Same current should flow. It need not be straight. I can
Ah.
bend the wire. This also in series
Mm.
because same current is
Mm.
flowing, right?
Ah.
Assume it's a water flowing pipe. Okay, the same pipe.
Mm.
So everywhere the water is
Mm.
similarly everywhere the current is same.
Okay.
But you have a second pipe like this, which is some amount of
Mm.
water flowing here. Then this part of
Mm.
the pipe and this part of the pipe are not in series.
Mm. So it deviates.
Yeah, current should be same.
Mm.
To put it simply.
Mm.
So in the case of water flow, so I can say this part and this part are in series. So if I
Mm.
make these two as a single pipe,
Mm.
then this and then this combined pipe and this these are in series.
Mm.
So the series the condition is current should be same.
Okay,
The
sir.
resistors are in series, then the current should be same in all the resistors.
All the resistance.
Here, R1, R2, R3, right?
Mm.
Whatever current is flowing here,
Yeah.
same current will come here, the same current will go here, go here, go here. There's no diversion, right?
Mm.
Same current is flowing through
Yeah.
everything. So these three are in series.
Yes, sir.
So Ohm's law you can apply to individual resistors. V1 is a drop across the first one, and the I is the
Mm.
current flowing through
Current flowing.
common current, which is same for all.
Mm.
So I into R1. So the drop across the second one is V2, it's IR2, V3. And this
Mm.
V is V1 plus V2 plus V3 because from here to here there is a rise of V and here there are drops.
Mm.
This rise should match
Ah.
with these drops according to KVL. Because if we take this closed
Okay.
loop, the net rise or net drop should be zero. So
Mm.
you should match with V1 plus V2 plus V3.
Okay, sir.
So in series, current is same and what is getting added is the voltage.
Mm.
Okay. And this V1 I can write in terms of individual resistors. You see,
Mm. Like I R.
yeah,
Mm.
Ohm's law apply to R1.
Mm.
V1 is potential across R1, right? So
Mm.
by applying Ohm's law to R1, I'll get this one and R2 and R3. Okay, so that I'll use here. So current is common. So that series
Mm.
combination I'll replace by single distance of value RS. Okay, and the
Mm.
same V and I should be there because only then
Mm.
I see equivalent
Yes, sir.
and replace by effectively allow the same current for the same resistance. So for the same voltage,
Mm.
obviously. So this
Mm.
V and this V should be same, and this I and I should be same. So once they are same,
Mm.
compare these two and write this one. Or I can put V here as I into RS and then cancel I'll get this result.
Mm. Mm. Like RS,
Yeah.
R1, R2. Mm.
So if there are n resistors, you just have to add them
Mm.
up to Rn. And if the n equal
Mm.
things, it's n into R.
Okay.
Because it's R plus R plus R plus R n times.
Mm.
And always when you have more resistors, the equivalent
Mm.
resistance value will increase. Suppose I add one more resistance R4 of value 0.5 ohms, the RS
Mm.
will increase by 0.5 compared to
Okay.
three of them.
Mm.
So in series combination, the combination is greater than
Mm.
any of the individual resistance, even the highest individual resistance also. Suppose here R
Okay.
is some 10 and this one is 1, this one is 0.5. RS is greater than 10
Mm.
also, 10 itself. Because
Mm.
10
The
plus
10R will be added on.
yeah, RS is greater than
Mm. R10.
RI, where I is 1 to 3
Mm.
for all I.
Mm. Mm.
Okay.
Mm.
Similarly, we can have resistors combined in parallel. This
Okay.
parallel combination, the condition for
Mm.
the way to check whether it's parallel or not is the potential drop across all the resistors should be same. Suppose the potential at this point is say, I call it point A, point B.
Mm.
So this is a
Mm.
connecting wire of zero resistance ideally. So this potential at this point is also
Okay.
VA.
Mm.
Potential at this point is also VA. Here also VA because these are all perfect
Mm.
connecting wires ideally. Okay. Potential at
Mm.
this point is VB. So the potential here is also VB. So potential across
Mm.
all the resistors is VA minus VB.
Mm.
V is higher potential because current is flowing in this direction. It will come here and it's split like this. Currents will not be equal because whatever resistance is
Because
less,
it deviates.
yeah, deviates, but if the resistance are
Mm,
equal, it will get split equally.
mm,
But if the resistance is
okay,
more, this resistance is less, obviously it will easy to flow through this path. So more current will flow.
okay. Mm,
Okay. So here what is getting added is the current. You can use KCL here.
and mm,
So I equal to I1 plus I2
I
plus
and
I3.
I3.
Entering current is
Mm,
I, leaving currents are the individual currents. Okay.
mm,
This is KCL. Okay.
mm,
And voltage is same, that I'll call as V. In the series
mm,
I was saying, I called as I. Okay.
mm,
So here that common voltage I'm calling as V. So Ohm's law I can use
mm,
to the individual resistor and get this one. And
mm,
here in this case, I'll put I1 as V by R1, VR2. And this
R1.
I'll replace by single resistance of value RP, okay, which
Mm,
should have the same VL. That's the minimum equivalent.
mm,
Okay. So for
mm,
that RP, if I use the Ohm's law, I'll get this one.
mm,
This I and this I are same. That is the condition
mm,
for it to be equivalent.
okay.
So once they are
Mm,
same, I just have to put I equal to V by RP in this one, cancel V, and I'll get
mm,
1 by RP equal to 1 by R1 plus 1 by R2 plus 1 by R3.
3. Okay.
Okay. So in series, resistance will add. In parallel, reciprocal will add.
There's an as reciprocal answer.
1 by R will add.
Mm,
Okay. In series, voltage will add. Current is same.
mm, mm,
In series,
mm,
voltages will add. Current is
mm,
same. Okay. In parallel, current will
mm,
add.
okay.
In series, voltage is getting split. The total voltage
Mm,
will get split here. In
mm,
parallel, current will get split.
mm,
Okay. So 1 by R will add. Just Ohm's law.
okay.
And then KCL.
Ah,
There also Ohm's law and then KVL.
mm,
So if you have n equal resistors, 1 by RP,
mm,
n times 1 by R. Think in terms of
N.
RP. In parallel, this thing, think in
Mm,
terms of 1 by R. Okay. So 1 by
mm,
RP is n times 1 by R.
mm,
Then you can take the reciprocal as R by n. So
alright.
in parallel combination, when I have
Mm,
more resistors, the
mm,
effective resistance will go down.
mm,
Okay, because 1 by R is going to increase. In
ah,
parallel combination, when I add more resistors, 1 by R will go up or 1 by RP will go up if I add more and more terms.
mm,
That means RP will go down.
mm.
Okay, so suppose I
So
have,
when we add a 1 by 1 by RP will be when we add, then RP will be decreasing also.
yeah, when you add more
Okay.
terms, 1 by R
Mm,
will increase, 1 by RP will increase.
okay.
That means RP is decreasing. Okay, we
RP is
can
decreasing.
understand physically like this. Suppose I have two resistors, 5 ohms and then 10 ohms.
Mm, mm,
10 ohms and second one is same 5, same 10.
mm, mm,
Okay, say this is third one is say 1000 ohms. Okay,
mm.
without thinking much, you will think the resistance of this one is more compared to this one, right? If you don't think much.
Ah,
See, understood? No, the first one is 5 and 10 in parallel.
5 and 10.
Second one is 5, 10, and then 1000 in parallel, 1000 ohms.
Mm,
So
ah,
you might think this resistance of this thing is more because of
yes,
1000,
sir.
but actually the resistance of this thing is less because we have a third path here. See, for here to go from here to here, I have two paths.
Mm,
Here
mm,
in the second one, in addition to two paths, I have a third path. So current is easy to
okay.
flow. Or I can assume like this: I have a third path here of
Mm,
finite resistance. That means
mm,
the path is not there.
mm,
So you have to compare 5, 10, and infinity in parallel with 5, 10, and
mm,
in parallel.
mm,
Okay. So in parallel, even if you had very high resistance in as a new resistor, the effective resistance will go
Go down.
because I'm creating one more path.
Mm.
But in the series case, I'm creating up. So if I add more resistor, the current will go from here to here. It has to go through this difficulty. It has to go through this
Mm.
third difficulty. If I add one more here, it's extra
Mm.
difficulty. The
Mm.
resistance will be more when I add more and more
Mm.
resistors. But here, when I add more and more resistors, I'm creating extra paths, additional
Mm.
fourth path. So GC for the current
Mm.
variable, this thing is 1 mega ohms, 10 to the 6 ohms.
Mm.
Understand mathematically, 1 by RP will increase by
Okay.
1 by N, 1 by mega.
In
That means RP
mm.
will decrease.
Decreases.
So that is one interesting point to note.
Mm.
In parallel combination, if we add more resistors, even if it's a very high value, we are actually making the
Mm.
current to flow
Another
easily.
path.
Yeah, you are making the current to
Okay.
flow easily.
Mm.
So here, R1, R2, R3, R4, are they in series or parallel?
Mm.
Which resistors are in series? R1, R2, R3, R4. Actually,
Mm.
what you can say is R1 and R2 are there in parallel
Ah.
because the voltage across R1 is voltage at this point and this point, which is same as the voltage here and voltage here.
Mm.
So these two are parallel.
Mm.
Okay, so I can combine this as one single RP1.
One RP1.
That I have to find out. 1 by RP1 is 1 by R1 plus 1 by R2. Okay.
Mm.
Similarly, R3 and R4 are parallel because the potential here and potential here are same drop here to here. Okay.
So
So
we
this,
need to note it as RP2.
yeah. So RP2.
Mm.
So make it a
Mm.
single resistance of value RP1. This one a single resistance of
Mm.
value RP2. Then these two are in series.
Mm.
So the effective resistance between these two, if I call it RS,
Mm.
that will be equal to RP1 plus RP2.
RP2.
Okay. So RP1 is 1 by R1 plus 1 by R2. RP2 is
Mm.
this one. And then R total.
1 by R. Okay.
In parallel, reciprocal will add.
Mm.
In series, resistance will add.
Resistance alarm.
Okay. So this I can complicate further. Instead of having two,
Mm.
I can have the third one here, R5. That
Mm.
means RP2 is 1 by R3 plus 1 by R4 plus 1 by R5.
5.
Okay. So
Mm.
here it is similar one. So here, how do you do it? How do you reduce it?
Mm. Same. So R3 and R1 are parallel.
No. See, the voltage here and voltage here are same, but this voltage and this voltage need not be same, no?
Oh. Then these are series parallels.
First, you have to combine these two. Do step by step.
Mm.
These two are in what?
Okay. So then it
No,
would
these
be
two are in
like
what?
RP.
No, these two are what?
Uh,
Series or parallel?
mm.
What? 1 and
Mm.
2, they are in series, right?
Mm.
So I can find R as
Yes.
well.
Then R1 plus R2.
Yeah, that's a
Mm.
single one which of value this one. Similarly, I can combine these two.
Mm. Same like RS 2 is equal to R3 plus R4.
And these two I can combine as 1 by R2 equal
1
to
by
1 by
mm.
R1 plus 1 by R2.
Mm.
So do step by step.
Mm.
These two are in series, so combine them and make it one. And then these two are in series,
Mm.
combine and make it one. So once you make it as a single
Mm.
resistance, then these two are in parallel.
Okay.
So I can also complicate this as a third resistance here, maybe fourth resistance here. So I can combine all these four as a single one, and I can have a
Mm.
third one here. Okay, I can combine this one. Okay, need not be here. I can have four resistors. Here I can have two resistors. Does not matter.
Mm.
So do step by
Okay.
step.
Okay, sir.
Difference between okay.
Mm.
So in parallel, less than the lowest
Mm.
resistance. So RP say R1, say 1 ohm, and this is second one is 0.1 ohm, and then third one is 5 ohms. So 1 by RP,
Mm.
or the combination RP, will be less than RI for all I.
Mm.
So it will be less than
Mm.
even 0.1 also.
Okay.
Okay, because if these things are not there, the resistance is 0.1, but having this thing have an additional path. So it's
Mm.
less than 0.1.
Okay.
Suppose this first one and third one are not there, then the resistance is 0.1.
Mm.
Now we have this extra paths, so resistance should be less than 0.1.
Less than 0.1.
Okay.
Okay.
In series, it's opposite. Suppose this is 0.1, this is 1, this is 5. So
5.
after going through the resistance of 0.1, I have to cross one more hurdle. I have to cross one more hurdle.
Mm.
So resistance is greater than 5 also.
Greater than 5.
Yeah.
But in parallel, the resistance will be lower.
Yeah. Less than the minimum one.
Minimum value. Okay.
Yeah. Here it is because 5 plus something.
Mm.
So here they have put more than highest resistance and less than the lowest resistance in parallel.
Lowest resistance. Okay.
Effective resistance, since the resistance is going down, so the current will be more.
Mm.
Their current will be,
As parallel will be low.
yeah. What they should say properly is in
Mm.
series one, as I keep adding resistors, the current will keep going down. In
Mm.
parallel, if I add resistors, more resistors, the current will increase.
Mm.
Because
Because
it's
those are parallel, so we can generate electricity faster.
not faster, resistors will go down. Is
Mm.
the same V,
Mm.
if R is less
Mm.
means I will go up.
Mm.
Because
Go. Mm.
V is I into R.
Ah.
Ohm's law. V is fixed. So
Yes.
if this thing is going down means this has to go up.
Go. Mm.
If I becomes I by 2, R should become 2R.
Mm. Mm.
Okay. So in parallel, resistance will go down if you have more and more resistors. In
Mm.
series, resistance will go up. So current will decrease.
Mm. Mm. Okay.
Yeah. In series, one of the resistors, suppose this thing breaks because of heating,
Mm.
excessive heating. So the current will stop here.
Mm.
In parallel, that's not a problem. Suppose this thing breaks because of excessive heating, two paths are there.
Then it goes to another part.
Yeah.
Mm.
So current will still flow in the main branch.
Okay.
So it's simple only. So the main thing
Mm.
is in series, the current will be same. In parallel,
Mm.
voltage will be same.
Mm.
That is the starting point. And the result is resistance will add in the series. And in parallel, 1 by R will add.
Mm.
Okay. Is it clear?
Yes, sir.
So heating effect means it's like similar to friction. Suppose I have this surface and there's a wooden block
Mm.
here. Okay. And the surface
Mm.
has got some friction. It's not a smooth one. So if I move this
Mm.
thing on this surface, there will be some heating, right? Because of
Mm.
friction. Even if you rub your hands, you will feel
Mm.
warm, right? That's because of friction.
Yes, sir.
Similarly, when
Mm.
charge is flowing in this wire, say copper wire,
Mm.
even though it's a good
Mm.
conductor, it's not zero resistance. Some resistance is there. Okay. What's
Mm.
actually flowing is the electrons. So if the current is flowing in this
Mm.
direction, electrons are moving in this opposite
Mm.
direction. So this will
Mm.
uh, actually the friction happens because copper atoms are there, no?
Mm. Yes, sir.
That is. So this electron will not go smoothly. It will go and hit this atom and then get deflected and
Mm.
then hit this one. Overall, it will go towards the right one, but it will go and hit in a
Mm.
hit somewhere zigzag way. So it will move towards left.
Yeah.
So whenever it hits something, it will lose some
Mm.
energy, which is getting converted to heat.
Okay.
Okay. So that heat is
Mm.
V to I.
Mm.
Suppose a current goes between point A and point B. The
Mm.
potential difference is
Mm.
say V is a higher
Mm.
potential, B is a low potential. So when current is flowing in this
Mm.
direction, through a drop of this one, the
Mm.
power or the heat dissipated will be V into I.
Okay.
Power. So energy is power into
Mm.
time.
Mm.
So heat is V into I into T. And if you
Meantime.
use resistor, suppose this thing is
Mm.
resistor, then this relation is valid according to Ohm's law.
Mm.
So I can write V as I into R. So heating will become I squared.
Yes. Okay.
This heating is called Joule heating.
Joule.
That's how a
Mm.
water heater works. You have a
Mm.
resistance coil, current is passed. So this resistance
Mm.
value is there. So because of that, I square
Mm.
R into T,
Mm.
it
Mm.
will go and heat the water, surrounding water.
Mm. And it will be hitting those water particles, sir.
No, not heating. Here it is,
Mm.
this thing will become hot. Temperature will go up.
Mm.
T2 and the water temperature is T1. So there will be a
Mm.
heat transfer from this coil to the water.
Okay.
Heating is happening inside this wire. That's not going to hit this water. This one. Yeah.
Okay.
After that is heat transfer.
Mm.
There's no electricity transfer. Once this
Mm. Okay.
once this coil gets heated up, then the heat transfer between this
Mm.
coil and the liquid water.
Mm. Mm.
Okay.
Okay, sir.
So this heat produces proportional to square of the current.
Mm.
Resistance value is fixed. Directly proportional to the resistance value. Okay. Proportional to the time. Obviously, if you need more energy to be passed, then time has to be increased.
More time has to be
In
increased.
1 second, the amount of heat transfer is V into I.
Mm.
So if you run for 5 minutes, it will be 5 into 60 seconds.
Okay, sir.
That into VA is the energy transfer.
Mm.
Actually, if you remember the definition of potential, it is the
Mm.
work done to move unit
By
charge.
time.
No, no. The first definition of potential, it's work done to move the charge
Mm.
with potential difference of V. Okay.
Mm.
Or potential is work done to move a unit charge. So whatever is the work done by the
Okay.
charge, that is the potential.
Mm.
So from this, the work done is V into Q, and work done per unit time, this I have to divide by T.
Oh,
That will become V into
okay.
I. That's how you get the power as V into I.
Mm. Oh, so you are dividing with the time.
Yeah,
Mm.
to get the power. Power
Okay,
is
sir.
energy per unit time. Energy is the
Mm.
work done in moving a charge through a potential difference of V. That is V into
Oh.
Q.
Mm.
Okay, that's different. That's discussed in the first part,
Yes, sir.
second section or something. Okay. So one application is a water heater or any other,
Mm.
wherever you want to heat the thing. Okay. Now
Mm.
this we can use this as a property to protect the circuit. Suppose these three resistors are there. Suppose instead of, see, if the resistance current is high means this resistance will break, right? Instead of that, I have a safety
Mm.
device like this here, which is fuse
Mm.
wire. Before this thing break,
Mm.
this thing will break because it's easy to replace this one.
Mm.
You have to replace the full resistance, no? Or some
Mm.
device. It can be heater also. The heater will get spoiled.
Okay.
Okay. So before this thing gets damaged, if I can
Mm.
cut this connection by
Mm.
fuse wire, then I'll protect this device.
Okay.
Because this device can take a maximum current of 5 amps, I'll make sure when this
Mm.
goes 4.9 amps, this thing
Mm.
will melt and break.
Okay.
So fuse wire is a wire which have a low melting point compared to this one,
Uh.
which will get
Okay.
damaged first before this thing gets damaged.
Mm.
So then I
Mm.
can fix the fault and put the fuse wire again.
Okay, sir.
Fuse wire connected in series with this device for
Mm.
circuit. When large current passes, the circuit fuse wire melts due to heating, high
Mm.
heating, and the current gets disconnected. Therefore, the
Mm.
circuit on the appliance are saved from damage. So fuse wire melting point should be low in the sense that
Mm.
the maximum current value, they should start melting.
Mm.
Only then this thing will break and the current will stop. Okay.
Okay, sir.
So the third application, actually nowadays you don't use these bulbs because it's consuming power. if you pass through this current through this thing, it's I square heating effect, right? I square R.
Yes, sir.
Okay, so this heat will make this thing red. If you heat a metal, it become
Mm,
red. After it become white hot,
mm,
once it becomes hot,
mm,
light will come out.
mm.
But
Yes,
actually,
sir.
heat also.
Mm.
When you touch those bulbs, it will be very hot.
Oh,
It turns out that this heat energy is very large. So that's why the efficiency
the
of,
large amount of heat, will be produced over it, sir.
yeah. So that's why it's not used
Oh.
nowadays. Instead of that, if you use
Mm.
LED, LED is a cool bulb.
Mm.
So heat is much
Yeah.
less
Lower.
compared to the bulb.
Mm.
So more energy will go into light.
Mm.
The same power here,
Mm.
if it is bulb means good amount of power is wasted in the heat.
Mm.
Okay, but if you use LED, that
Mm.
heating is very less. So
Yes,
most
sir.
of the power is going to this producing light. So with less power
Mm.
here, I can get the same amount of light.
Okay.
So that's why actually these things are not used nowadays.
Mm.